Hello and welcome to part 2 of Dev Maths and Stats Refresher Course, Lecture 4. Now here we're looking at angles between vectors. Before we look at the angles between these three vectors here, just want to point out something about angles between vectors. Actually, we should just have a look at these applets. So here we go, another demonstration if you're finding it difficult to visualize the vectors in 3 dimensions. I recommend you have a look at this one, which lets you change the coordinates. So in this one here, if you change the x coordinates, we can make it come out of the screen towards us. Sometimes it's easier if you see this. This then shows you the x coordinate, the y coordinate, and the z coordinate. So if I then move it, the z coordinate down like this, then it's pointing downwards. If I move the y coordinate back, it's pointing like that. If I move the x coordinate back in, you can always make it point away from us. Yeah, so you can change the 3 components around. You should get a feel for how the components affect the direction of the vector. Oops. But this is the one I want to look at now, just to show you quickly what I mean by the angle between 2 vectors. So here you've got, when it loads, so here we've got x, y and z axis, and we've just drawn 2 lines in space here. You can see that there's the angle we're trying to find. Now the problem is, it's hard to judge the angle because you can see they've measured it and it's 98.17 degrees, so it's more than the right angle. But if you move it around like that, there it looks much bigger there. If you put it at that kind of angle, it looks bigger. I'm spinning madly. But if you put it at this kind of angle, it looks narrower than it really is. So what you need to do to judge the angle properly, you need to try and get it so you're looking from this kind of angle. So you're looking straight down onto it. If you imagine that they are on a flat surface, you want to look down onto it to get the correct angle. Oops. So you just need to be a bit careful when we go back to here to try and judge the angle correctly. So what I want to do is to look at the angles between the red and the green and the blue lines. I want to categorize the angles. Now, we go back to here. I've got in here the 3 lines. So that's the red line, the green line and the blue line, x, y and z. Now hopefully what you can also remember from previous experience of doing maths is this, that where you have angles, there are several possibilities. Oops. And the easiest one. Now, if you look at angles, there's a name for these angles. And what I like to do with students is to ask them if they can remember the names of these. Most people can remember that this one is called right angle. Otherwise known as 90 degrees. Otherwise known as, a special word for this is orthogonal. So these 2 lines are orthogonal, or at right angles, or at 90 degrees. In this situation here we have less than 90 degrees, and this is more than 90 degrees. And more than 90 degrees is known as an obtuse angle. Less than 90 degrees is known as acute angle. In my favourite film, somebody says that they have acute awareness. Anyway, that's another story. So we can categorise all angles between 2 lines as less than 90 degrees, acute, equal to 90 degrees, right angle, orthogonal, or greater than 90 degrees, obtuse, when they're kind of pointing in away from each other like this. So the question is now, which category are the angles between this and this? So we want the angle between x and y. Great, that's a good start. Should be systematic x. So the angle between x and y, what angle is that? And what's the angle between y and z? So the angle between x and y is the first one. Now if you had access to Maple, you could have a look at this yourself, so I just have to explore it for you. I'm looking for the angle between these two lines here. And if I go something like this, hopefully I can persuade you that however you turn it, the angle between these two is less than 90 degrees. So this is an acute angle between these two. So back on here, we can put acute, less than 90 degrees. Okay, so we look next at x and z, which are the red and the blue lines. So if we look at the red and the blue, that's this line and this line. So the red and the blue, I think however I turn it, it seems that the angle between the red and the blue lines, this and this, is greater than 90. Okay, greater than 90 degrees. So the angle between these two lines is obtuse. It is greater than 90 degrees. And the angle between y and z, well, you might be able to guess what it is, but let's do it anyway. So that's between the green and the blue lines. This one, if I get the correct angle there, should be able to persuade you is exactly 90 degrees. That's a bit more like it there. Yeah. Yes, there we go, that's the right angle. So the angle between the green and the blue is exactly 90 degrees. So this is, let's say, right angle. So these are orthogonal. Let me just make a little bit more space here. So dot product of x and y is this times this, so 5 times 3 is 15. So 15, subtract 4 is 11, and then this gives you nothing, so this comes to 11. Dot product of x and z is 5 times minus 1 is negative 5. Negative 2 gives you negative 7. 0, so that's negative 7. And then y and z comes to 3 times negative 1 is negative 3. 4 times 2 is 8, so negative 2 plus 8 is positive 5. Subtract 5 is 0. So now if we compare these, we see that the acute angle comes out as 11, obtuse minus 7, the right angle is 0. Now, the takeaway from this that's critical is that when there's an acute angle between any two vectors, the dot product will be positive. So it'll be always positive for any two vectors. It'll always be negative when the angle is obtuse, when they're pointing away from each other like this. So negative means they're pointing in this kind of direction. Positive is this kind of direction, negative is this kind of direction. But the one that's completely critical for optimization is this one. When any two vectors have dot product 0, they are pointing at right angles, they are orthogonal. So that's a really easy way to tell that two vectors are at right angles, is to do the calculation and see if you get 0 In that case, you have a right angle. Okay, hopefully that's clear from there. Now, what I recommend you do is, maybe after the lecture at some point, look at these visualizations here. There's some more visualizations of the dot product here. These first two are very similar. The first one reminds you of how you get them. So this is A, B, C, D. That's the definition of the dot product. It's A times C plus B times D. And you can move these both around. And you see that when it's green, it's acute, so always positive. So pointing in the same kind of direction, or the angle is less than 90. If they're pointing sort of away from each other, like this, then the angle is, this is negative because we have an obtuse angle. But any time it comes to exactly 90, then it's always going to be 0. Can't get it to be 0 exactly there, but there's one. Okay, so when they're at 90 degrees, there's 0. This one does a similar thing, except it puts in the way of calculating it using trigonometry, which is it's the length of this times the length of this times the cosine of the angle between them. So if you know trigonometry, that's how you work it out. If you know the length of the vectors, it's this length plus times the cosine of that. And because the cosine, cos of a 90 degrees is 0, that's why it's always 0 when they're at right angles. And finally, this is quite a useful one because this shows another interpretation of dot product is the dot product of A and B. It says something about how far does A go in this direction. So we choose how A is this length, but in this direction it only goes this far. And dots, so it's quite a long vector, but it does not go very far in this direction. Whereas if they're pointing in similar, if the angle is small, vector A goes quite a long way in the direction of B. And actually, the dot product gives you almost exactly that, as long as you would have to divide by the length of B to remove the effect of that length. And that gives you the length, the distance that A goes in the direction of B. That's another interpretation of dot products. And there's another useful one here, which just shows you that an interpretation of when you add together two vectors. So here's vector u, and there's vector u and vector v in 3 dimensions. Yeah. And it also shows you, as well as vector u and vector v, it shows you vector u plus v is here. So u plus v is if you go u and then start from here and go along to do parallel to vector v, you get to here. Or you can do first v and then do vector u, you get to the same place. But all of these vectors are sort of trapped within this plane. So wherever you can move vector u and vector v around, but wherever you move it, they are within the same plane. You can't get out of that plane by adding them together, which is also quite a useful concept. So as you move one of the two vectors, that flat surface, that plane moves. And all the combinations of u and v are entirely in that plane. And the last thing I won't go into now, because this is just for interest to show you there is another way to define two vectors being multiplied. This is called the scalar, this is called the vector product, because the answer is a vector instead of a scalar. But it's much less used, and certainly not used very much in social science. But just to let you know that's there. Okay, so next part of the lecture we'll go on to matrices, but for now, thanks for watching.